Hello everyone, and welcome to the online lecture for college algebra. In this video, we're going to cover section 2.1 on an introduction to functions. So let's start by addressing the question, what actually is a function? And by definition, a function is essentially a rule or a set of instructions that assigns each element from a set of inputs called the domain to a unique output in a set called the range. And it's really that word unique that makes a function what it is. Each input gets assigned to a single unique output. So you can't have one input going to multiple different outputs. And we'll put some numbers to this shortly, don't worry. To begin with, we're going to start by talking about what are called discrete functions. And a discrete function is just a set of ordered pairs in which no two ordered pairs with the same first coordinate have a different second coordinate. So let's describe what we mean by that. So a discrete function is just a list of ordered pairs. If you were to graph a discrete function, it would just be a bunch of dots. So let's say we have 2, 3, we have 4, 7, and maybe 6, 9. Then we let the first coordinate of each ordered pair represent the input of the function. That would be part of the domain, and we'll get to more on that shortly. Whereas the second coordinate would be the output of the function. So for this function in particular, if you were to put in an input of 2, it would transform it into an output of 3. So that brings us back to this word unique output. Because you can have just tons of sets of ordered pairs, is whatever ordered pairs you want to. They all qualify as what is called a relationship. But a function is a special type of relationship where you have unique outputs. And so if no one input can be assigned to multiple different outputs, that means you can't have repeated first coordinates. So if you had, say, 2, 3, 2, 5, 4, 7, this one would not represent a function because you have the input of 2 giving you two different outputs, 3 and 5. And that violates the uniqueness part of the definition. Whereas on the other hand, if no first coordinate repeats, then that's fine. 2 has a unique output of 3, 4 has a unique output of 7, 6 has a unique output of 9. So this is a function. Now I'll try to refer to them as first coordinates and second coordinates because we haven't assigned any variables to this yet, but later on we're commonly going to call the inputs x and the outputs y. So if you think of these as a traditional ordered pair x, y, it's a function if no x value repeats with a different y value. All right, so example 1 is pretty straightforward. Given the following discrete relationships, determine whether or not they represent a function. Do those first coordinates repeat? So take a second, pause the video here, and see if you can find the answer to part A through C. Just yes or no. So for part A, no first coordinate repeats, unique outputs. This is a function, yes. For part B, on the other hand, you've got an input of 9 giving you two different outputs, -3 and +3. So this does not represent a function. That's no good. For the last problem, we've got a table, but this is still ordered pairs, and now we've assigned variables x and y. So these are still just the ordered pairs 1, 3, 2, 3, and 4, 9. So the question is, does this list of ordered pairs represent a function? And you'll notice that the 3's repeat in this case, But that's fine. All we care about is, do the x's repeat with different y's? And because 1, 2, and 4 are all different, 1 has a unique output, 2 has a unique output for 2, and 4 only goes to 1 output, yes, this does represent a function. No x value repeats with a different y value. So now let's talk a little bit more about domain and range. So remember, when I was giving you the definition of a function, I said that the set of inputs was called the domain, and the set of outputs is called the range. Well, for a discrete function, for lists of ordered pairs, we assume that the first coordinate is the input and the second coordinate is the output. So the domain of a discrete function is just a list of all of the first coordinates, or a list of all of the x values if you think of it in terms of x, y. The range, the set of outputs, is just a list of all second coordinates, or all y values if you think of it in terms of x and y. All right, so domain are the x's, range are the y's. Now, when you do assign variables to a function, like in that table in part C, or like my ordered pair xy here, the variable associated with the domain or the inputs is called the independent variable, because that's what you choose to plug in, and you can choose whatever you want to, it's independent. Whereas the variable associated with the outputs or the range is called the dependent variable, because its value depends on the first coordinate, right? That's what the function does. It takes your input of x, turns it into an output of y. So y depends on what value of x you plugged in. So example 2 then is just an extension of example 1. We're asked to find the domain and range of the following. And again, it's just a list. So for part A, if we want the domain, it's the list of all x values of all first coordinates. So it would be -1, 2, and 3. Those are the possible inputs for the function. Whereas the range would be the set of all second coordinates, outputs, which also happen to be, in this case, -1, 2, and 3. So try pausing the video here and see if you can find the domain and range for the function in part B. So the domain, set of all x values, which in this case is 1, 2, and 4. The range is the set of all y values, and we don't list repeats. There's only 2 numbers in the range, and that is 3 and 9. Right? So given a discrete function, the set of all inputs or x values, first coordinates, is the domain. The set of all outputs or y values is the range. But domain and range isn't purely restricted to functions. Relationships have domains and range as well. So in C here, we have this relationship that we decided was not a function in example 1, because that 9 repeated with different outputs. It didn't have a unique output. But you can still find the domain and range of the relationship. So once again, try pausing the video here and find the domain and range to the relationship in part C. So the domain, the set of all first coordinates, would just be 9, 4, and 0. Technically, it doesn't matter what order you write these in, but if you would like it to be easy for the reader, you might write them in ascending order from smallest to biggest. And then the range would be the set of all y coordinates, which would be -3, +3, 2, and 0. And I'll go ahead and write these in order to begin with. We've got -3, 0, positive 2, and positive 3. Anytime your range is bigger than your domain like this, that's a sign that it's not actually a function, because the only way that can happen is if one element in the domain mapped to two different elements in the range. But again, all you have to do is check if any of the first coordinates repeat. Up until now, we've been looking exclusively at what are called discrete relationships or discrete functions, lists of ordered pairs. Now we're going to shift gears a little bit and start talking about continuous relationships or continuous functions. So these are not going to be defined at just discrete x values or whatever variable you're looking at anymore. It's going to be defined over entire intervals of values. So let's just take, for example, the interval from 1 to 2. If you want to have a continuous function here, you have to have an output for 1, you have to have an output for 2. But on top of that, you have to have an output for 1.5 because that's in the interval. You've also got to have an output for 1.1, for 1.01, for 1.001. All of those are in this interval. And in fact, there are infinitely many numbers between 1 and 2 because you can just include as many decimal places as you want to. And so our function can't be defined as just a list of ordered pairs anymore because there would be infinitely many in the list. So instead, we define continuous functions by equations. So if a function is a rule that assigns a certain input to a unique output, we define continuous equations in terms of the instructions for how that's done. So if we have the function y is equal to 2x plus 3, what this is saying is it's giving you the set of instructions or the rule for turning an input into an output. You take your input, you double it, multiply it by 2, and then you add 3 to it to get the output. And you can do that for any value between 1 and 2. The graph of a relationship or a function is simply the collection of all ordered pairs that satisfy the equation associated with it, or in the case of a discrete function, just the set of all ordered pairs, period, defined by the function. But again, this means infinitely many ordered pairs. Any x and y that would make this true is part of the graph, which is why we end up with one continuous curve. Infinitely many ordered pairs go into making this shape what it is. So let's talk about how we understand whether a continuous relationship represents a function or not. For the discrete case, we didn't want any x values to repeat. What about for the continuous case? Well, truth be told, the idea is exactly the same. So let's say, for example, we've got two ordered pairs, 1, 3, and 1, negative 2. If this were in a list of a relationship, a discrete relationship, we would say this is not a function because that x value, that input, repeats with two different y values. Graphically speaking then, if I were to graph both of these ordered pairs, 1, 3, and 1, negative 2, to have two ordered pairs that violate the definition of a function, they have to both be on the same vertical line. So to determine if an equation represents a function, we look at its graph, or at least that's one way to go about it. And we do something called the vertical line test. The graph of a relationship represents a function if and only if there is no vertical line that crosses the graph more than once. If a vertical line intersects with 2 points on the graph, that's a situation then that does not represent a function. So let's take a look at a few graphs, and I'm going to ask you the question, is it a function? If it passes the vertical line test, it's a function, it works. If it doesn't, it's not. So let's start with this graph, and this is a shape called an ellipse. And so the question is it a function? And quite simply, the answer is no. Because you have a vertical line that passes through the graph more than once. And all it takes is 1 point. One spot where a vertical line passes through more than once. So an ellipse is not a function. You could still write this as an equation. You could have a relationship between x and y. It's just not that special relationship that we call a function. Next up, we got what looks like a pretty standard cubic polynomial. And so the question is it a function? And the answer is yes. This function gets really steep, but it is always moving to the right, always moving to the left. So no matter what, anywhere you draw a vertical line, it will only intersect this graph exactly once. And so yes, this does represent a function. And we got one more. This is a shape called a hyperbola. And the question is it a function? And once again, since this fails the vertical line test, the answer is no. This graph does not represent a function. So now let's talk about something called function notation and function evaluation. In a lot of our applications, we have needs of referring back to functions quickly, or maybe we're working with more than one function in a single problem. And so because of that, it's very useful to be able to give them names. And so we name them with letters. So for example, I could take this discrete function of ordered pairs 2, 5, and 3, 8, and I could give it the name f. You could actually name it whatever you want to. You could name it the function g. You could name it the function h. You could even name them with capital letters if you want to. And we do that in some applications. Right? Any letter you can let represent the name of a function. Well, then in this case, since the function f takes an input of 2 and pairs it with an output of 5, in function notation, we say f of 2 is equal to 5. And that's the way you would read this. F of 2 is 5, or is equal to 5. All right, so the thing in parentheses next to the function's name is the input, or the x value, if you think of it in terms of x and y. And the thing on the other side of the equal sign is the output, or the y value, if you think of it in terms of x and y. Similarly, with this particular discrete function, we could say f of 3 is equal to 8. Input of 3 goes to an output of 8. So that's how we handle discrete functions. We just give them the name, whatever we want, whatever letter we desire. For a continuous function, we do something similar, although we keep that parentheses x next to it this time around. We let f of x, or whatever letter of x, represent the value of the second coordinate or output. So f of x would be the y value of the function. And so that means that f of x is equivalent to y. And you can use them interchangeably for graphing and function notation. So if I take the line y is equal to 2x plus 8, that is a function. It's just a line, and its graph passes the vertical line test. I can just replace y with f of x to write in function notation f of x is equal to 2x plus 8. Now, if I want to figure out what f of 2 is in this case, f of 2, that's basically telling me everywhere I have an x in my equation, I'm going to plug in this input of 2. Right? So it's just telling you what to plug in for x, the thing in parentheses. Now, if you want to be safe, what you want to do is you want to start by taking your x in your equation and replacing it with parentheses, and then plug whatever is inside of these parentheses in where x used to be, because we're going to get to plugging in some more complicated stuff than just a single number shortly. And so in this case, f of 2 would be equal to 2 times 2, which is 4 plus 8, or an output of 12. F of 2 is 12. And again, it's important to note this thing in parentheses would be the x value. This output would be the y value. So this would correspond to the ordered pair 2, 12. So let's work some examples involving function evaluation. And for example 3, we're only going to be plugging numbers in to the functions. And so we've got two functions here. We've got f, which is a discrete defined function, and we've got g, which is a continuous function. And we can certainly mix and match as well. So for part A, we're asked, what is f of 4? So given the function f, you would look for an input of 4. F will transform that into an output of 5. F of 4 is equal to 5. Right? Similar for g of 4. So we're going to look at the function g, and everywhere we have an x, we're going to replace it with 4, which would give us 12 plus 5, or 17. And I want you to notice something here, because this is going to be important. If you plug a number into a function, you get a number out of the function. Plug in a number, get out a number. Part C is a little bit trickier, because it's asking you what is x if g of x is equal to negative 4. So they're asking you for the x value, and they're giving you the y value. G of x, this whole left-hand side of the equation this time, is negative 4. So this is the setup for an equation. G of x is negative 4. That's equal to 3x plus 5. And now we just want to solve this for x. So if we subtract 5 from both sides, we'd have negative 9 is equal to 3x. And then if we divide by 3, we would have x is equal to negative 3. So they swapped it on us. They gave us the output, and they asked us to use that to solve for the input. And then last but not least, in part D, we've got a combination of the two, but you still just evaluate each one individually. F of 3 minus g of 3. So let's start with the f of 3. This is just like part A. So f takes an input of 3 and turns it into an output of 8. This is going to be minus g of 3. Let's work that out. So for g of 3, I plug in 3 for x. So that would be 9 plus 5, or 14. And so f of 3 minus g of 3 is 8 minus 14, or a negative 6. But there's no rule saying you just have to put numbers inside of functions, at least not continuous functions. This wouldn't work so well with the discrete functions. So now what we're going to do is we're going to take and plug in other variables or even other expressions into the functions and see how we handle that. So we've got two functions in this problem. F of x is 3x squared minus x, and g of x is 4x minus 2. In part A, we're asked to find f of w. So again, what that's saying is everywhere you have an x in the function f, we're just going to replace it with the letter w. So this would be 3 times w, still squared, minus w. Part B is a little bit trickier. We've got g of 8 minus 5, and this is where the parentheses are really going to start to come into play. Anytime you have a negative number in here, or anytime you have an expression with a lot going on like this, replace your variable with parentheses. So what I'm going to do is I'm going to take the x and g, And I'm going to replace it with a minus 5. But when I do, it needs to be 4 times all of that. So this is going to be 4 times all of a minus 5 still with the minus 2 on the end. And now I'm going to simplify. So if I distribute through, this is a 4a minus 20, still with the minus 2. And so that would give us 4a minus 22. Now, I want you to pay close attention to something here. In the previous example, example 3, we took note of the fact that when we plugged a number into a function, we got a number out of the function. Now we are plugging letters into the function, and what we get out is a new function. It's not a number this time around. For some reason, when I ask a question like this on an exam, once students get here, it's a pretty common mistake that they will set this equal to 0 and try to solve for the variable. This is not equal to 0. You cannot do that. If you're asked to do function evaluation with a letter, you should expect a new equation out. And then last but not least, we've got part C, g of x plus 2 minus g of x. And I say last but not least, but there's a part D to this problem as well. And once again, we're just going to evaluate each individually. We don't even have to evaluate that because g of x is just the function itself. So let's start by doing the g of x plus 2. So everywhere there's an x in g, I'm going to replace it with x plus 2. This is the same as part B. So if I distribute and combine like terms, that's going to be 4x plus 6. Another thing to be a little bit careful about, this g of x, I'm about to replace it with multiple terms. Because of the subtraction out front, I need parentheses for this, minus all of g of x. And g of x is just the 4x minus 2. Now I can simplify. So this is a 4x plus 6. If I distribute the minus sign through, minus a 4x minus a negative 2, so plus 2. The 4x's cancel, and we get an 8 out. Now we just got a number output this time, but that's just happenstance. It just happened to work out that way that the 4x's canceled with each other. It's not guaranteed to happen. And in fact, if I had adjusted this to something like g of 2x plus 2, then they wouldn't have canceled in this manner. So let's take a look at one more example of this function evaluation, and this is going to be kind of the peak. This one's going to get a little bit messy. And so we're asked to find f of x plus h minus f of x divided by h. And this is actually something called the difference quotient. For the function f, which we don't really get into here in Math 101, but it is very important for math overall because this becomes the basis of the definition for something we call the derivative and all of differential calculus. We're just asked to do some function evaluation though, so we can handle that. So break it up into parts again. Let's start with this thing in the top left, f of x plus h. Right, so everywhere there is an x in the function f, and there's 2 of them, I'm going to replace with parentheses x plus h. So this would be 3 times x plus h quantity squared minus all of x plus h. Now there's a lot of simplification to be done in this one. So to start with, this x plus h quantity squared, I need to FOIL. Order of operations, PEMDAS. The exponent's going to become first here because I can't simplify the stuff in parentheses. And so if we FOIL this out, you would have x times x, or x squared, plus x times h, plus x times h, plus h times h, or h squared. So this is all still times 3, but when you FOIL this out, you get x squared plus 2xh plus h squared. And then I'm also going to go ahead and distribute the minus sign through those parentheses. That's going to be a minus x minus h. And then last but not least, I need to distribute the 3 through the parentheses. So that would give me 3 times x squared plus 6 times xh plus 3h squared, still with this minus x minus h at the end. No like terms here, no unique combinations, or rather no combinations of x and h to the same power, so that's as good as it gets. And again, all of this is just this number in the top left. But that's really what we needed here. Everything else is going to be a little bit easier to handle. So I'm going to plug all of this into the top left. 3x squared plus 6xh plus 3h squared minus x minus h. Now, in the top right, I still need to subtract off f of x, which we know exactly. That's just the function itself, 3x squared minus x. But it is minus the whole thing. So minus all of 3x squared minus x. And all of this is still over h, which is a variable. We just have to carry it through as h. It'll be part of our final answer. So now let's see if we can't simplify a little bit. And we're actually going to be able to. So if we distribute this minus sign through on the top, this becomes a minus 3x squared plus x. So we have a positive 3x squared and a minus 3x squared, which cancel. And we have a minus x and a plus x, which cancel. So that leaves me then with 6xh plus 3h squared minus h over h. So we just have the 3 terms left in the numerator. But then you'll notice that there's an h in common between every term in this fraction, so we can reduce. If I factor an h out of the numerator, that would leave me with 6x plus 3h to the first power minus 1. And then that will reduce. And so this is as simple as it gets. This is our final answer. 6x plus 3h minus 1. All right, so a lot of algebra in this problem, but this is function evaluation potentially at its most messiest because you had to keep track of 2 variables in this problem, which meant a lot of stuff did not simplify along the way. Or at the very least, it's the messiest it's going to be in this class. All right, so last but not least, earlier in the section, we talked about how to find the domain and range of a discrete function. Domain were just the first coordinates, x values essentially. The range were the second coordinates, or the y values. Now let's talk about how to find the domain of a continuous function based off of its equation. And it's not just going to be a list anymore, it's going to be an interval of x values. So we're going to bring back the interval notation from section 1.7. In general, we all agree that if the domain of a function is not specifically stated, then the domain is all real number inputs that will give a real number output. So any real number x that you could plug in that would give you a real number y is part of the domain. Well, oftentimes instead what we do is we look for what doesn't work. What could you plug in that wouldn't give you a real number output? We call those restrictions. And so the domain will be all real numbers except for those restrictions. Now, in general, the restrictions you need to watch out for in this section is that you don't want to divide by 0, because if you do, that gives you undefined. Undefined is not a real number output. And you don't want to take the square root of a negative number, because that gives you an imaginary output, not a real number output. So i's are valuable for solving equations, but now that we're dealing with functions, we don't want imaginary outputs. Those are not part of the domain. All right, later on, we will add more restrictions to this once we get to chapter 4 of the book. So in example 5, we're going to be asked to find the domain of many functions. And again, the thing to watch out for is dividing by 0 and square root of a negative number. Dividing by 0 only ever occurs if you have x's in denominators, or whatever variable you might be working with at the time. And square root of a negative number, you usually only have to watch out for if you have x's inside of square roots. So these are the situations where you're going to have to lay restrictions. So with that said, let's think about part A. Y is equal to 3x plus 2. Well, no matter what real number you plug in for x, if you multiply it by 3, it's still a real number. And if you add 2, it's still going to be a real number. So in other words, you're never going to divide by 0 if you plug in a real number, and you're never going to take the square root of a negative number. So there are no restrictions. The domain of this is all real numbers, or as an interval of x's, that would be from negative infinity to positive infinity. Part B, on the other hand, we have an x in a denominator. So now we have to be a little bit more worried. So we've got y is equal to 4 over x squared minus 49, which if you want, you could factor into x plus 7 times x minus 7. We don't want to divide by 0. The two x values that would cause you to divide by 0, and remember, you can always set the equation not equal to 0, or set the denominator not equal to 0 and solve it as an equation if you're having trouble seeing it. But negative 7 would cause the left parentheses to be 0. That's no good. And positive 7 would cause the right parenthesis to be 0. So we don't want that. So our domain then would be all real numbers except plus or minus 7. So that's a verbal description of the domain. Let's think about this then in interval notation. And this gets a little bit tricky. I think using a number line to help picture it really helps. So we're saying that the domain is all real numbers except for a gap at negative 7 and a gap at positive 7. Two holes in the domain. This breaks the number line up into 3 regions, 3 intervals. And so the domain of this function in interval notation would be negative infinity to negative 7, parentheses, because negative 7 itself is not included, it's a hole in the domain. The one in the middle would be from negative 7 to positive 7 with parentheses. And the one on the right would be from positive 7 to positive infinity. And then just like with the inequalities, we join those pieces of the answer together with the union symbol. And so this is what it looks like when you have an entire number line from negative infinity to positive infinity, but with a gap at negative 7 and with a gap at positive 7. Common mistake here is that students just tend to forget the one in the middle. Negative 7 to positive 7 gets left off here pretty frequently. For part C, we've got a quadratic function. F of x is equal to x squared plus 2x minus 3. And once again, no x's in denominators, no x's in square roots. No restrictions for this one either. This domain is also all real numbers. And in fact, any polynomial will always have a domain of all real numbers. They never have restrictions. Let's take a look at a few more. So in part D, we've got y is equal to the square root of 5 minus x. And we've got a variable inside of a square root. So we need to be careful here. We don't want to take the square root of a negative number. And so the way we do that is this time around, we're not going to look for restrictions. We're just going to straight up look for what is okay, what works. So we're going to take the radicand, everything inside of the square root, and say after you combine all this together, the number has to be greater than or equal to 0. It has to be 0 or positive. It can't be negative. And so that gives us a simple linear inequality that we can solve for x. So if I subtract 5 from both sides, and then divide both sides by -1, that flips the direction of the inequality. This is x less than or equal to 5, or the domain in interval notation would be from -infinity to 5 with a bracket, because 5 is okay. Square root of 0 is okay. It's just 0. It's only square root of negative numbers that we don't want. And so you'll find that with square root functions, you'll always end up with a piece of the number line, whereas with the rational functions, like 1 over x squared minus 49, you end up with the entire number line, but with gaps in it. So it looks a little bit different. Same thing for part E, although you're going to notice in this case, we don't care about what's going on outside of the absolute value, or excuse me, outside of the square root. All we care about is that the inside of the square root is not negative. So try pausing the video here and see if you can find the domain for part E of example 5. All right, so same as before, I'm going to say the inside of the square root, x plus 2, has to be greater than or equal to 0, not negative. Well, this is pretty easy. We just subtract 2 from both sides to get x is greater than or equal to -2. And so in interval notation, this one would be from -2 to positive infinity. Then last but not least, in part F, we've got y is equal to the absolute value of x plus 5. And absolute values don't give us any trouble. No matter what real number you plug in for x, its absolute value is also a real number. If you add 5 to that, it's still a real number. So absolute value functions also have a domain of all real numbers, or from -infinity to positive infinity. And that is it for section 2.1, our introduction to functions. In terms of problem types you should expect from this section, given a discrete relationship, so a list of ordered pairs, you should be able to determine if it's a function, right? No x value can repeat. And you should be able to find its domain and range. Those are pretty easy problems once you understand how to do them. The second type of problem is, given a graph, you should be able to determine if that graph represents a function, and that is the vertical line test. The vertical line test is very important, so make sure you know what it means and how to perform it. For part 3, the third type of problem, that's function evaluation. So given functions, be able to evaluate the functions at both numbers and expressions. Sometimes it's really easy. Sometimes, like we saw with the difference quotient problem, it can be pretty tricky. And then last but not least, given an equation, you should be able to find the domain of a polynomial function, a rational function, a square root function, or an absolute value function. And in particular, it's the rational and the square root where you end up having to set restrictions. And remember why you're setting those restrictions, because it will help you set up the domain. For rational functions, don't divide by 0. For square root functions, don't take the square root of a negative number. The inside of the square root has to be greater than or equal to 0. With that said, as always, if you guys have any questions, please make sure you let me know, and I will see you in the next video.